Howdy. In this example, we're going to practice how to reduce a simple distributed loading. Take a look at this problem. So what we have over here is a simply supported beam, here in black, and there's some loading acting on it. Hopefully by now you can recognize all these downward arrows as a distributed loading, right? So we have some distributed loading acting on that beam. But then we have other types of loading. We have here a point load of 10 kilonewton going down right at this point, 4.5 meters away from this point, which we'll go ahead and label maybe point A. And this one here, we'll call it point B. Anyway, so going back to the problem, we have simply distributed a beam, we have distributed load, we have a point load, and we also have a couple moment over here with magnitude of 45 kilonewtons meter. Our job for today is going to be to replace the loading acting on the beam, right? So the distributed, the point load, and the couple moment, all the three types of loading that we know how to deal with by now. We want to replace all of those with a single resultant force, and we also want to specify where that resultant acts relative to point O. So this is a combination problem. Combination, I mean, we have to do the simplification and then the further simplification of force and couple system, while also having to reduce the simple distributed loading into point loads. Now, do you remember when we're dealing with distributed loading, what is the first step? Correct. The first step is going to be to divide this distributed loading into simple shapes. So in this example, I can think of dividing this like this. So from the 10 kilonewton point, or 4.5 meters away from point A and onward in that direction, we have a constant distributed load, right? So it would make sense to make a cut here. Over here, I have a triangular loading, right? But it doesn't go all the way to zero. So what I can do, nonetheless, is if I continue, this line is supposed to be straight, sorry. Right? I can divide this into two simple shapes. This triangle up on top, and then a rectangular strip that goes from point A all the way through point B, right? Here, some people might be tempted to call this one the triangle, a rectangular strip to this point, and then this other rectangular strip. So dividing into three simple shapes. That would not change the answer. As long as we do everything correctly, it doesn't matter into how many simple shapes we divide, right? The advice is always to divide into the least amount possible that's going to simplify your life. So again, what I will do over here is first the strip. Maybe we do this one first, and then we'll do the triangle. We'll call it a simple area number 2. So let's calculate the areas. First, for the rectangular strip, the area is fairly easy, right? The area of a rectangle is just the base times the height. Right? So in this example, what is the size of the base? Well, we have 4.5, and we're going to add 1.5 to it. So 4 plus 1 is 5, plus half and half, that's 6 meters. So we have 6 meters as the base. And then the height, what is the height of this rectangular strip? Again, the height we always equate it to the magnitude of the distributed loading. So right at this point, these are telling us, or the problem is telling us that it's at 3 kilonewtons per meter. So 3 kilonewtons per meter. Again, when we multiply this base, which has units of distance, times the height, which has units of a force per distance, right? The meter is going to cancel with the meter, and we're going to have units of kilonewtons. Here specifically is 6 times 3, or 18 kilonewtons. Next, let's go ahead and calculate the area of the triangle. Right, area of a triangle is 1/2 the base times the height. So here we're gonna have 1/2. The base is 4.5. meters. And what is the height of the triangle? Here you might be tempted just to look at this high point over here and say, oh, it's 6 kilonewtons meters. But remember, we already divided into simple shapes, right? So all of this up to this point has been taken care of from the rectangular, right? So really the height of the triangle is from this point up, right? So 6 minus the value of this point, which is 3, is going to be 3 kilonewtons per meter, right? Again, when we multiply, this meter is going to cancel with meter, and that's going to give us an answer in kilonewtons. So 0.5 times 4.5 times 3 gives 6.75. So let's go ahead and do a new free body diagram. In this new free body diagram, let me do like this. That's point A. Over here is point B. Right? And if you remember from the previous video, what we want to do is when we calculate these areas, now we have the resultant, right? The same force as that distributed loading. And we want to place it on this beam over here. Because again, the math that we know how to do is with the point loads. So we have that the area, right, of the rectangle is 18 kilonewtons. So I know I can substitute this rectangular distributed loading strip with just 18 kilonewtons. Now the question is going to be, where do I put it, right? So the location of that force is going to be at the centroid of that area, right? So this being a rectangle, the centroid is going to be right at the middle or half of the base. Well, the base we said was 6, right? So half of the base is 3. So if this is 4.5 somewhere here, we can place the 18 kilonewtons from the rectangle. Again, this is half of the base. So from point A to this 18, I need to go 3 meters. Which is that guy. Next, we'll go ahead and put here the equivalent or the resultant of this distributed load from the triangle, which is 6.75, right? The 6.75, that is the magnitude. The next question is, what is the location where we're going to put it, right? It's going to be at the centroid. This happens to be a right triangle, so the centroid of a right triangle is 1/3 of the base from the right angle. So since the right angle is over here, if we move 1/3 of the base that way, that's where we locate the centroid. The base is 4.5, right? If we divide by 3, that gives us 1.5. So this 6.75 force is going to be 1.5 meters from point A. So remember, the previous one was 3. This is going to be right at the half. So this from the triangle, 6.75 kilonewtons. And this one is 1.5 meters away from point A. Right? But these are not the only loads that we have. We also have this 10 kilonewton load. So this one, I'm just going to put it over here. Right? We're not doing anything yet. So we have 10 kilonewtons. The distance from point A to the 10 kilonewtons is going to be this original distance, 4.5 meters. Again, why am I basing all the distances relative to point A? Because the problem wants to simplify all of these loads with a single resultant force relative to point A. So it makes sense that when I'm calculating the distances, to do so relative to that point A. Okay, so what have we done so far? We replaced the rectangular distributed loading, the triangular, with these 2 point loads, right? We have this 10 kilonewton point load. I'm putting it at the original point again. All that we have left is this couple moment of 45 kilonewton meters, which happens around this point B. So again, this is an equivalent force system to this one, has the same external effects on the body. However, what we want to do is we want to simplify to a single resultant force. To be able to do that, first we have to do simplification, so that then we can do the further simplification. So the first simplification is to simplify all of this into a single resultant force and couple moment acting at point A. How do we do that? Again, the answer is in the solution. We need to find the single resultant force. So the resultant force, go with the black marker, right, is just the sum of all the forces. Normally, we would be summing all the forces in the x and summing all the forces in the y. In this example, all the forces here oriented in the y direction. Let's assume here this is x horizontal and the y is vertical, right? So this is going to be 0. Sum of the forces in the x gives 0, and all we have to worry about is some of the forces in the y. So what do we have in the y direction? We have 6.75, 18, and 10 kilonewtons. These are all forces that are pointing down. So if you're following the convention where we say, look, a force is positive if it points up, really we have minus 6.75, minus 18, and minus 10. The 45 kilonewton meter is a couple, right? We're summing forces, only these are forces, this is a couple. We cannot add a couple here. So we type this in the calculator, we get minus or negative 6.75 minus 18 minus 10. This gives minus 34.75. Again, because we were using our convention here that a positive force points up, this negative just means the resultant has to go down. Alternatively, you could have done it by inspection and just added 6.75 plus 18 plus 10, knowing that all the force is pointing down. So that means that when you add that total, right, that resultant force has to point down. So we have something like this. That's our resultant force, 34.75. The units are kilonewton. So we calculated the resultant force. Next, we need to calculate the resultant moment at point A. So do you remember the formula? Resultant moment at point A is just going to be the sum of the moments at point A plus any couples. Remember, this first term is what we're capturing with the first one is some of the moments at point A. So we're looking at the body and we're asking the question, are we summing any moments caused by a force that does not pass through point A? So the 675, the 18, and the 10 do not pass through point A. So each of those is going to generate a tendency to rotate. So all of these are going to capture here, plus any couple moments. In this example, we have one. It's 45 kilonewton meter. So let's go ahead and begin calculating. Again, the way I like to do these when I'm summing moments at a point is I like to start at that point, and usually I'll sweep to the right over here. So if I'm going that way, right, I'm starting at point A, I'm going to go that way. The first force that I encounter is 675. So the force is 675. The distance to the force is 1.5, right? And notice I'm not worrying about signs. I'm not calling the 675 a negative force, right? Because what we're summing is moments. So all I want is the magnitude of the force, right? The magnitude of the distance, if you want to think of it like that. the sign is going to come from the direction of the rotation that that force generates. Remember, our convention is always that it's positive if it's counterclockwise. So if it creates a counterclockwise, it's positive. The 675 about this point A, right? If I'm at point A and I pin and I go down, this guy's gonna rotate clockwise or negative, right? So that's gonna be a negative moment, right? So if this guy produces a negative moment, the 18 force is gonna produce a negative moment, the 10 is gonna produce a negative moment. So minus 18 times the distance from point A, which is 3. And then we have the 10 kilonewton, right? We're going to subtract again because it creates a negative moment. So the force is 10. The distance is 4.5. And I hope you can appreciate why I was doing this free body diagram and I was getting all the distances relative to point A when we were locating the centroids of these areas. It becomes very easy to plug it in this equation. So I have the 675, the 18, and the 10 force, this one, and this one. There's no other forces that can create a moment, right? So next, we're done with these. The next term that I have to worry about is any existing couple moments. I already say we already have one, right? This 45 kilonewtons. So I have to add it, right? But it's not just I add it, is I need to look at it and say, is this going to be a positive couple or a negative couple moment? Because if it was oriented in the negative, if it meant the body, if it tried to rotate the body clockwise, I wouldn't necessarily add it, I would subtract it. In this case, because this couple moment, right, is oriented in the positive direction, I am going to add it, and this just adds as 45. I don't need to multiply it, right, because that's already a moment. It already has units of force times distance, right? All of these have units of force times distance, and all the units of the force are in kilonewtons, and all the distances are in meters. So this is kilonewton meter, kilonewton meter, kilonewton meter, kilonewton meter. So if I just add all of that in the calculator, this is going to give me the resultant couple moment at point A. So we will negative 6.75 times 1.5 minus 18 times 3 minus 10 times 4.5 plus 45. All of that is going to equal minus 64.125. Remember, this is going to have units of kilonewton meter. Now there's look here, we got a negative number, right? We're sticking to our convention. So what this means is that the resultant couple moment is negative or clockwise. Like so. So I have a lot of those forces producing negative moments. I just have one producing a positive. What this is saying is that all of these combined are bigger than this other one. And it makes sense because look at this one. 10 kilonewtons times 4.5, right? This is going to be 45 kilonewton meter. That's negative, this is positive. So essentially, the moment produced by this force from the distance to point A cancels with that one. And what we're seeing in this minus 64.125 is just the contribution of these two. Because again, this one is going to cancel with that one. Anyways, the number that we got from this equation is minus 64. So that means that this moment is going to rotate clockwise. It's going to rotate like this. And it has a magnitude of 64.125 kilonewton meter. We're almost done here. We've simplified this. We've simplified the distributed loads into point loads, and then we took all the point loads and couple moments into a single resultant force and couple moment. However, we want just a resultant force, no couple, right? So for this, we need to further simplify. You remember how we do this, right? So we want to move this resultant force to the left or to the right from point A, such that when I move it a distance, this force is going to cause the same tendency to rotate as this couple moment. Here it's pretty obvious to see that because the couple moment is clockwise, I need to move this force here forward so it creates a clockwise rotation. So again, I want to put it somewhere here. This resultant force, 34.75 kilonewtons. The question that we need to answer is specify where it acts relative to point A. So another way of saying that is give me the distance to that force from point A. So remember, moment is force times distance. So therefore, the distance is the moment divided by the force. Specifically, the one we're replacing is the resultant moment at point A, and we're replacing it with the resultant over here. So the resultant moment at point A is 64.125, and the resultant force, right? So if I divide by 34.75, which is the resultant force, I get a distance, hopefully I didn't make a mistake here, of 1.84. So this D is 1.84 meters, right? And it's going to be to the right of our point A over here. This is point A. So at this point, I want to remind you that when I typed it in, I just used the magnitudes, right? The magnitude and the force. Yes, this is a negative moment because it's clockwise, so I could have typed in the calculator negative resultant moment. But again, if you're going to use the signs, you can't just use it on top and ignore the 1 for the force, right? If you're going to type this as a negative moment over here like we got, you got to remember that this resultant force in the y was negative. So negative divided by negative, it becomes a positive. I always suggest you forget about the signs for these types of calculations and just visually inspect and tell me, okay, if I move this way, it's going to create that rotation. So I'm just looking for the magnitude of that distance. So just use the magnitude of the moment, magnitude of the force. It's going to work out because you already determined and you need to go forward and not back. So there's no need to worry about the signs for the D. So no need to plug them in there. So I really hope that you found this video useful. Please let me and everybody know in the comments below if you found any mistakes in the calculations. And otherwise, I'll see you on the next one.